Hey everyone, this is Dr. Clyde Letzum again, and today we're going to be looking at Coulomb's Law in this video, and specifically Coulomb's Law for an apparatus that we will be using in our lab. And so here's a scenario that we are setting up. We have a suspended sphere here, and this sphere is made out of metal coating. Okay, it has a metal coating on the outside, and we have a guided sphere here that we're going to move towards this suspended sphere, and this is also made of the same metal coating. Now the thing is this guided sphere actually has been charged, so it's been negatively charged, so there's an excess of negative charges on it. When we bring that close to the suspended sphere here, what we expect is that because the outside is coated with metal, we expect that electrons from the outer shell of the atoms that are closer on this end are going to actually move to the other end. Now you'll notice that I show here that we have 4 negative charges and 4 positive charges. This is saying that the ball as a whole is neutral. However, though, it's been polarized because we have positive atoms that are mostly positively charged over on this end, and atoms that are mostly negatively charged on this end. Now, given that this is a scenario and we're moving this sphere in here, what's going to happen then is the suspended sphere is going to be attracted towards the guided sphere here, and they're going to end up touching. All right. And so after they touch, what's going to happen is the suspended sphere is going to now pick up 2 of the negative charges from the excess 4 negative charges that were over on the guided sphere. And so we'll have 2 excess negative charges on this guided sphere, and we'd have 2 negative charges on this guided sphere. Now you'll notice that this guided sphere here has been deflected by an angle of theta, and this is a very, very small angle for our experiment, very small angle. Okay, and the reason why I'm mentioning that is because that's going to become important in a little bit. All right, so now if we look at the free body diagram for such a scenario where, again, the ball has been deflected by a very small angle, what you'll know is that in order for the ball to move over to the right side here, there must be some sort of electrostatic force that's actually pushing the ball over in that direction. So in terms of our X components here, we have an electrostatic force that's pointing to the right. We also have the weight of the ball itself, which is actually going to be pulling downward in a negative Y direction. Now in terms of our string here, remember there was a string that was keeping the ball here suspended, this suspended sphere. All right. This string has tension in it. Because it has tension in it, and the tension is actually going in this direction, heading up towards the point where the ball is connected, then what we know is that if we were to break that tension into its components, we would have a tension in the Y direction that's pointing upwards, and we would have a tension going in the negative X direction here. So again, a tension going in the positive Y direction, and we have a component for the tension going in the negative X component, or negative X direction in this case. So again, when I combine all this information together and I look at Newton's law here, in order to describe what the forces are in the Y direction and the X direction, what we're going to have is a Ty, tension Y component going in the positive Y direction, and we're going to get the weight, of course, pulling down in the negative Y direction. Now note that when the ball gets to this point, it's not going to move. It's just going to be deflected to that point, and it's just going to remain there. So therefore then the acceleration will be equal to 0, and so we can say Ty minus W is equal to 0. In the X direction, again, we have the tension, the X component of the tension going towards the left here, or in a negative direction, and we have F of E going in the positive direction. So because of that, we may write that Fe minus Tx is equal to 0, and again, the ball is just going to be suspended there. It's not going to go very far from there. So recall that W, which is our weight, is equal to m times g. And in this case, since we're looking at the angle in here, all right, what happens then is our ty component then, which is this component here, all right, is actually going to be equal to t cosine, all right, of theta, all right, t cosine of theta. And that's because this component here it's parallel. Okay, we can say it's parallel to this angle in here, so therefore it makes it adjacent to that, right? And so that's why we end up with cosine. So it's t cosine theta is equal to ty. Now, if we substitute all this information into our first equation up here, we get that t cosine theta is t cosine theta minus mg is equal to 0. All right. And so when we solve, we can actually solve for t in this case and find that t is equal to m times g divided by cosine theta. Now, as far as our x components is concerned, all right, we can actually take our t of x. Now, t of x is going to be equal, meaning the x component of the tension is going to be equal to tension times sine of theta. And the reason that's sine of theta is because this theta, or pardon me, this component here is opposite to this angle. And so therefore, we have to use sine in order to figure out its component. So once we've done that, we can replace our t of x from up here into our equation and put that in here. So now this equation becomes fe minus t sine theta, which is equal to 0. Again, 0 because it's not moving. All right, so now because that's equal to 0, we can say that F of E, which is that electrostatic force, is equal to T sine theta. Now, you may or may not recall that Fe, okay, we can actually now take this equation in here. We can take this equation and replace our tension here with mg cosine theta, and that came from right here, okay, and then that will be equal to sine. And if you remember your trigonometry equivalence, sine theta over cosine theta is actually going to give you tan of theta. So our electrostatic force here is actually equal to m times g times tan theta. Okay, now, so what is tan theta? So tan theta, if that angle in between here, all right, is really small, we can say that tan theta is actually approximately equal to d divided by L. So if you remember SOHCAHTOA, the tangent is equal to opposite over adjacent. So if we're dealing with this angle in here, the opposite is this d over the adjacent, which is this L. Okay, and so therefore then our tan is approximately equal to that. Okay, approximately in this case, and that's only the case if theta is really small. If theta becomes larger than that, then we have a problem. But for the purposes of our experiment, we're just going to assume that they are about the same, okay, or theta is really small. So if we know the mass of the ball now, the mass of the ball that was suspended, then we can calculate the electrostatic force, or electric force, by using the equation Fe is equal to mg tan theta, where tan theta can actually be replaced by d divided by L. So this is our electrostatic force, or electric force, okay, that caused the ball to be pushed in this direction. Now, given that information, if you all remember Coulombs Law, Coulombs Law stated that electrostatic force, or electric force, is equal to K Q1 times Q2 divided by R squared, where K is what we call the Coulombs Law constant, which is approximately 9.0 times 10 to the 9th newtons meter squared divided by Coulomb squared. Okay? And Q is the charge on each of the spheres that we were talking about a little bit earlier. So remember, we had two spheres. We had that suspended sphere and we had the guided sphere. Okay? Now the radius here, or R, is actually the distance between the two spheres when the ball was actually deflected. Okay, distance between the two spheres when the ball was deflected. So now, using that information, we can actually put those two equations together, the one that we developed earlier, which is m times g, times D divided by L, which is an electrostatic force of this problem, is also equal to Coulomb's law equation here. And so we can manipulate this down to the point where we get that Q, all of this now is equal to Q1 times Q2. Again, one of our Q's is the charge on one ball, one is the charge on the other ball. Now, if you recall, at the end, remember when the two of the balls touch, what happens was each one of them had the exact same charge on them. So we can actually say then that Q1 and Q2 are actually equal to each other because those are, again, the charge on each one of the balls, right? And they were equal at the end. So therefore, then each ball at the end will have a charge, which is Q, equal to square root of M times G times D divided by L times R squared, all of that divided by K, and then we take the square root of that. So we can actually find a charge as long as we know that distance between the two balls at the end. Okay, if we know the length of the string, if we know how far the ball was deflected, if we know the mass times the grams, or in other words, the weight of the ball, and we also know, again, we know what Coulomb's law constant is. So this is how we're actually going to use our information in this lab in order to figure out how to find the charge on each of the balls in our Coulomb's law apparatus. All right, so again, this was a discussion on Coulomb's law and how we're going to be looking at using Coulomb's law for our experiment. Again, my name is Dr. Clyde Letzum. You can visit my website, and you can also visit my YouTube channel. If you like what you see here, please do give me a thumbs up.